In continuation to the lectures on integration, my today's topic is integration by parts. First question is, when do we use integration by parts? And the answer to this question is,
whenever we have integral of the form fx into gx means product of two functions, we require a formula to find integral of product of two functions.
in differentiation, you have already done how to find derivative of product of two functions, and derivative of product of two functions is equals to first into derivative of second plus second into derivative of first. My question is, why this rule cannot be used in integration?
Let us consider integral of u into v is equals to u into integral of v plus v into integral of u, means if we consider that it follows the same formula as of differentiation, let's see what happens. Differentiating both sides with respect to x, this is what we'll get. We know that differentiation and integration are reverse process of each other. It means on the left hand side we'll be left with only uv, and on the right hand side to both the terms I will apply the product rule, and this is what I'll obtain. Again, differentiation and integration, reverse process of integration, and the second term on RHS will be v, and the last term on RHS will be only u, and this is what we'll obtain. If we compare LHS and RHS, it is not true. Hence, the formula is wrong and cannot be applied in integration.
So friends, in this slide we saw that left hand side is not equal to right hand side, means this formula cannot be applied. If this method cannot be applied, then what should be the formula to find integral of product of two functions? Let us see.
Let's try to derive integral of uv from the formula of derivatives which we already have. We know that derivative of uv is equals to u into derivative of v plus v into derivative of u. Let us integrate both sides, LHS and RHS. We'll be left with only uv in LHS. Let us leave RHS as it is in the first step. Let's rearrange the terms, and we will obtain integral of u times dv upon dx is equals to uv minus integral of v du upon dx. Now let's consider that u is equal to fx, dv upon dx is equal to gx, which implies if u is equal to fx, then derivative of u will be f dash x, and if dv upon dx is gx, then v will be integral of gx, because again integration differentiation are reverse process of each other. Substituting all these values, now let us convert u and v in terms of f and g on both the sides of the last step. This is what we'll obtain. We'll be left with integral of fx into gx is equal to fx times integral of gx minus integral of gx f dash x dx. So we got the formula for integral of product of two functions, which is also written as integral of first into second function is equal to first into integral of second minus integral of derivative of first into integral of second. So this is the derivation how we obtain the formula for product of two functions.
So ultimately, integral of first function into second function is equals to first into integral of second minus integral of derivative of first into integral of second. So amazing, we got the formula to find integral of product of two functions, which is known as integration by parts. Now next question is, can the same formula be applied in all the cases? Answer is no. The formula cannot be used in all the cases. Example, integral of root of x sine x. We cannot find integral of root of x sine x because there does not exist any function whose derivative is root of x sine x, since we have already done that integration is a reverse process of differentiation. Now let's see the formula which we have derived, whether it satisfies the definition of integration or not. That is, derivatives and integration are reverse process of each other.
Let's verify the given formula obtained. Check whether it satisfies the definition of integration or not. Let us differentiate both sides with respect to x. Left hand side will be only 1 into 2, and on the right hand side, first term I will apply product of two functions, and second term on RHS, again derivative and integral will cancel each other, and this is what we will obtain. And now if you observe carefully, in first term again differentiation and integration will cancel each other. First term will be 1 into 2, and second and third terms are exactly same, will cancel out, and this is what we will get. It means this formula also satisfies the definition of integration, that is, integral is a reverse process of differentiation.
Using the derived formula, let's try to solve a problem.
Integral of x into sine x. Here I will take x as first function and sine x as second function. Applying the formula, I will get first into integral of second minus integral of derivative of first into integral of second. Integral of sine x is minus cos x, derivative of x is 1. Substituting, this is what I will get after the step, and the minus minus in the second term will become plus. Integral of cos x in the second term will become sine x, and the answer is minus x cos x plus sine x plus a constant of integration. Remember one more thing, constant of integration will come only once in the last step. You don't have to put the constant every time you integrate. If you observe in the formula, integral comes thrice, but we are not going to write constant.
Using the same formula, if we take sine x as first function and x as second function, will we able to solve the problem? Let's try to find out.
If sine x is taken as first function, x as second function, applying by parts, we will get sine x into integral of x dx minus integral of derivative of sine x into integral of x dx. And we know that integral of x is x square upon 2. Derivative of sine x is cos x, and after first step, this is what we will obtain. Now, look at the second term on RHS, which has become more complicated. The degree of x has increased. It means if I keep on applying the formula, sine will get converted into cos, cos will get converted into sine, but degree of x will keep on increasing, and I will not get any final result.
It means that the order of function is very important to us. Means order matters a lot. Which function we are taking as first function and which function we are going to take as second function affects the answer. So we have seen that since the order in which we are taking first and second function is important to us, then how do we select that which function will be taken as first function and which function to be taken as second function? The method to remember is, just remember I late, and here is a rule.
I late. I stands for inverse trigonometric functions, L for logarithmic, A algebraic, T trigonometric, and E for exponential functions. This is the order in which we select first and second function for by parts.
The question is it necessary to
Every
use this
time,
rule?
but
Can't we solve the problem
only in the end.
without using this rule? Answer is no, it is not necessary to use this rule. This rule is just for our convenience. Moreover, if one function is given to us, still we can use integration by parts, still we can multiply that function by 1, and we can use the method of by parts. For example, let's see how to find integral of logarithmic function.
In order to find the integral of log x, I will multiply log x by 1, and I will take log x as first function and 1 as second function. Applying by parts, this is what I will get. First into integral of second minus integral of derivative of first into integral of second. I know integral of 1 is x and derivative of log x is 1 upon x. This is what I will get after this step. Cancelling x in the second term, and I'll be left with only 1 in the second term, and integral of 1 is x. So answer will be.
With the similar method, we can also find the integral of all inverse trigonometric function. Here is a 1, tan inverse x.
In case of tan inverse x, again I'll multiply tan inverse x by 1. I'll get 1 into tan inverse x dx. I will take 1 as second function, tan inverse x as first function, and applying by parts I will get first into integral of second minus integral of derivative of first into integral of second. We know that integral of 1 is x and the derivative of tan inverse x is 1 upon 1 plus x square. Substituting, this is what we'll get in the next step. Now second term on right hand side, if you observe, derivative of denominator is 2x, so I shall multiply and divide the term, second term, by 2, and this is what I'll obtain, x times tan inverse x minus half integral of 2 upon 1 plus x square x times dx. Second term on RHS I will consider as half of I2, and I will solve I2 separately in order to simplify. So this is I2. I2 is integral of 2 upon 1 plus x square x dx. If I consider denominator as t, numerator is derivative of denominator, and we have already discussed whenever numerator is derivative of denominator, integral is nothing but log of denominator. Hence I2 will be log of t, that is log of 1 plus x square, and I2 will become log of 1 plus x square plus a constant, and our integral is x times tan inverse x minus half log of 1 plus x square plus constant of integration.
So in this video we discuss how to find integrals using by part. In my next video we shall discuss integral of few more types, and that video will be the last part of definite integrals. Thank you.